Hello, this is Tim Fox, and this is a circuit simulation of an 8-bit CPU which implements my Does One Thing, or DOT ISA, which was designed to run a short program that calculates and stores 100 numbers and their bit widths into two arrays. So this is an 8-bit register, and it's used as a building block for my program counter and register file. And here is the program counter. Now, this is the instruction memory, and I have 4 different memories that I can select from, and I can use the program counter to cycle through each instruction. And here's a register file which has 1 write port and 2 read ports. And I have a data memory. It holds 256 bytes. And I used D flip-flops here to adjust the timing of the writing and the reading to match that of the other instructions. Here's the ALU. It is mainly used for adding data or calculating memory addresses. I have a couple of special circuits which are used to implement a couple special instructions in my ISA. This is for my init instruction, and what it does is it places 2 bits of data in one of 4 selectable positions. And then I have a circuit here which calculates the bit width of an 8-bit number. Now here's the control unit, and it uses the opcode and data from the 2 registers RX and RY specified by each instruction, and it calculates desired results using the ALU and the bit width and init in parallel with each other. And then we get an address and an instruction result. So finally, the instruction memory, the register file, the control unit, and the data memory are all here, and they have their inputs and outputs connected to each other in the appropriate places to create the CPU. And then I also have this top level view, which is just useful for presenting and debugging the CPU. This is test case V1 of the array width program. So when I manually run the clock, R1 fills with 1, R2 fills with 1, and R3 fills with -1. Then R1 and R2 are added together. The result is stored in R1, and then it is XORed with the -1 in register 3. Then that number is stored in data memory at R0 as an offset plus hexadecimal 0. And then finally the width of that number is stored into data memory at R0 plus hexadecimal 80. And finally R0 is incremented by 1 to change the offset for storing into data memory. Now I will run the clock automatically until the end of the program. So now that R0 has reached 100 or hexadecimal 64, you can see the halt instruction has been called. And I can turn off the clock now. I can dump the data memory by setting this to 1 and then pull up the console in Firefox with Control-Shift-K. And we're able to view an array of the first 100 numbers that were calculated. And then starting at address 128, we have the widths of each of the 100 numbers. Now I can clear all the registers in data memory back to 0. And I can select test case V2 of the array width program. So I'll manually run the clock again to show the first few steps. And then I will let it run automatically till the end of the program. So again, R0 has reached 0x64, and the halt instruction was called. And we can dump the data memory again and check the browser's console. So for test case V2, we have the first 100 numbers. And then again, starting at address 128, we have the widths of all of those 100 numbers.